So maybe still let me begin. So I'm thankful to organize this, especially to Javier for the invitation. So I have to say two things. So firstly, this is based on joint work with Yuri Drost. Secondly, the work I'm going to talk about is not new at all. So,
no, he's coming. He got it. He's going to be here in a second.
Well, but still, let me keep. So I'm sure that Javier knows. At least, or should I wait? So maybe Andras, you are the second organizer. Should I wait for Javier?
Wait 1 minute.
I'm
Wait 1
honored.
minute. But we're not in a rush.
Well, anyway.
You are the only speaker, so you can tell us the story.
Exactly. So the story is such that this results were announced 2007. So the final version was published 2017. So of course we did in the time not only this thing, so there was revision. We worked out on details, but still, so it is a work which took some efforts for us, and the reason we were asked to present it here is that there will be talk of Kingmin on Friday, where there will be a mirror symmetry continuation of the started story. So let me.
This is, I already have a question. So this is a hypersurface case, or this is just any surface singularity with minus and any? So it doesn't matter.
No. I'm going to be actually very careful. So let me first recall the definition of maximal Cohen-Macaulay module. So I see the most of the audience knows it anyway. So for any Noetherian ring of Kroll dimension equal to D, let me denote by K as a residue field. And the category of maximal Cohen-Macaulay modules so, and when I say Cohen-Macaulay modules, I mean maximal ones. So these are those finitely generated modules which satisfy the following vanishing property. With the residue field, so it should be 0 for all I between 0 and D. So it's a formal definition, and maybe let me recall you that if A is regular, then this category is basically trivial. Maximal Cohen-Macaulay modules are regular ones. So this category of Cohen-Macaulay modules is only interesting if we indeed have a singularity. It's kind of a homological measure or complicated the singularity is. Well, today, I concentrate on the case of surface singularities. And in this case, let me recall the result of saying that a surface singularity is normal if and only if it is isolated and Cohen-Macaulay. So a ring is Cohen-Macaulay if it is Cohen-Macaulay is a module of itself. Moreover, so I think it was already mentioned by Augusto, that in this case the category of Cohen-Macaulay modules is the same as the category of reflexion modules. So modules which are isomorphic to its double dual. So I'm going to present now some construction valid for all non-insulated Cohen-Macaulay surface singularities. So now let me say that A is non-isolated. On Macaulay surface. And well, strictly speaking, it's not important at all places, but for the sake of convenience, let me assume completeness. So I will tell you. Maybe the only place, well, there are two places where I will benefit from it. So I like categories which are Frischlet, guaranteed by completeness, for instance. And I also, well, need some extra conditions which guarantee finiteness of the normalization. So that R is a normalization of A. So integral closure in the total ring of fractions.
So is irreducible in your? Do we have a? You cannot know that you can define normalization.
Well, I think you're right. I think you're right indeed. I do not want nilpotence. But should I don't know. So if I have a surface singularity which is Macaulay, it can also reduced. So reduced is an assumption. Also, maybe, so let us look. So actually now I even suspect that spin reduced is not essential. But well, let's assume it. So anyway, so I want some condition which guarantees me finiteness of the normalization over the ring. So there are some tautological examples where it is not so, but never in the complete case, never in the geometric case. Okay, so an important object associated with this setting is a so-called conductor ideal. So it is annihilator of R modulo A. So concretely, it is the set of those A in A such that R times R is in A. And from this characterization, it is easy to see that conductor ideal is ideal in the normalization, but also it is, of course, ideal in the ring A itself. The second observation is the following. So I claim that this ideal is Cohen-Macaulay viewed as a module over A over R, and for this it is useful to observe that there is an isomorphism from here to home, from R to A, and the map is organized as follows. So if we have an element A here, so I attach to it a map lambda A from R to A. So mapping R to the product A. And one can check that it is indeed a bijection, so it is an isomorphism, which allows to conclude what I mentioned before, that I is Cohen-Macaulay module over A, because it is home between the Cohen-Macaulay models. So in the sophist case, being of this form guarantees Cohen-Macaulayness, and it is also basic commutative algebra, saying that if I have a finite ring extension in a module, Cohen-Macaulay over bigger ring is the same as Cohen-Macaulay over small ring. Having another conclusion that I can now take quotients. So of course I have an inclusion here. Well, I is precisely ideal, well, describing the non-normal locus of my non-isolated singularity. So all dimension drops. The dimension of I bar is 1, dimension of R bar is 1, and it's going Macaulay again by basic commutative algebra. So the depth drops most by 1, so they are both going Macaulay. And as a consequence, they have regular elements, and it is going to be important. So I take now the corresponding total rings of fractions. So they could contain nilpotents actually, but it's not bad. So these are Archimedean rings. And I have such an inclusion. All right, so what I do with this next, so let me summarize what we constructed so far. So I have ring normalization. I can mod out the conductor ideal, and I can here go to the total ring of quotients of I bar and R bar. Well, and it is a commutative diagram in the category of rings I am going to work with. So one more thing. So in the case of surfaces, I can also speak about normalization of Cohen-Macaulay module. Which is the following modification of the tensor product. So I induce my module, so it can have torsion, but if I take the reflexive hull, then I get a maximal Cohen-Macaulay module over the normalization, and it is obvious that this operation is functorial. So now I want actually to do the following thing. So I want to implement the following idea. So assume I have a Cohen-Macaulay module M, then I can normalize it. I can consider tensor product over Q of A bar, and well, these two objects meet on the common territory. Here, when I go to the modules over Q over R bar, however, the results are not isomorphic. So results are not isomorphic, but related. And if my module M is Cohen-Macaulay over A, then so let me write it in a full way. So So without this taking reflexive hull, so it is obviously an island. But when I take reflexive hull, so I can do it. And I get a surjective map. So because on surfaces, when I go from a module to reflexive hull, kernel has finite maps. And let me give a name to this morphism and call it theta m. So theta m is a surjective homomorphism of Q of our models. So now I want to implement the following idea formally. So I want to say that I can reconstruct a Cohen-Macaulay model from some data, sort of from this model, and the way how this model match on the common territory. And let me now make it formal. So I define now the following category, which we called category of triples. Well, which is defined only involving the unisolated surface singularity A. So objects are triples. So what I want to do? So I take. So maybe let me make a step back and still write a diagram involving categories and functors. So have a functor from the category of Cohen-Macaulay models over A to the category of Cohen-Macaulay models over the normalization. I have the usual tensor product. As well as tensor product here. Well, compositions of both functors are not isomorphic, but there is a natural transformation. So in the category theory, notation like this is like this. So there is a natural transformation from one composition to another, which is given by this family of maps theta. So I have such a transformation of functors. Well, now the idea which I want to implement, so I am coming back.
Sorry,
Yes.
theta inverse direction.
No. So I go from this direction to this direction. So theta.
No, theta.
Huh?
I mean this theta.
Well, here is the for module M.
The diagram.
Why? Ah, yeah. So of course you are right. Right. Sure. Actually, I'm not sure. So how to?
Correct.
It was correct. So yeah. I think so. And right. So the idea is that we can reconstruct the category of Cohen-Macaulay modules. Well, just from this part of the diagram in blue. And the idea is the following. So my triple consists of an object N, which is Cohen-Macaulay over R, of some module V, and from a map making a link between them. And this map.
The theta,
Yes.
what you have on the left is an R model, a QR model,
Right.
not QA model.
Sure. Wait. I'm just saying.
The diagram.
You. So just please just try and wait and then I explain. So this theta will be used in the theory. So it is my theta. So I have a Cohen-Macaulay module over Q of I bar. So they meet. So I want my theta to be a model homomorphism and surjective. And there is one extra condition. So here, actually, I have some adjunctions. And a constraint is that if I take canonical morphism from V to this tensor product sending an element of V to 1 times V, then I want that composed map is injected. So these are my objects, and morphisms, well, so the definition of morphism is very natural. So whenever we have a pair of functors with the same target, we can always speak about the so-called comma category. And concretely, so if I have one triple and another one, so then what is a morphism? So I want to have a morphism from V1 to V2. I will want to have a morphism from N1 to N2. And they have to match this link map. So the way to arrange it is the following. What my theta 1 is, so I write what my theta 2 is. So, and I want compatibilities of F and G. So I require that the diagram involving these maps is compatible. So, in this way, I defined a category Now a theorem which I proved together with Yuri Drozd asserts that the category of triples and the category of Cohen-Macaulay modules are actually equivalent, and equivalence is given by the following one. I take a Cohen-Macaulay module M, and then I take its normalization. So I pull it on the total rank of quotients of A bar, and then there is this map theta M. So now theta M is, so this theta M is surjective, and then it also satisfies this additional property stated above. So it is an equivalence of categories, saying that when I, for instance, I want to classify Cohen-Macaulay modules over A, I can speak about equivalent classification problems here. Well, and the main point is that it is indeed a progress. So this category of triples turns out to be more accessible in some cases, and it is what I wish to explain now. So I would like now to discuss one very characteristic example.
So the dimension two or only dimension two.
Yes. Okay. And coming back to the question of Anders, so now, so of course I have to go through all the proof, but I do not see where on the level of formulations I used my singularities reduced. But somehow I do not want to guarantee it. So maybe it's even, it could be true also in a full generality.
I have a question.
Yes.
So you used conductor ideas.
Yes.
And what role does it play when you make the quotient?
Well, let's discuss an example. So, because without an example, it does not look very convincing. But here is a singularity, which also you studied. So, let me take a surface singularity, which is a degenerate cusp. So it is a singularity of type T to 3 infinity. So Chalhun and his collaborators, Suzaramani, I remember, Kulmin, but also Kungmo, so also discussed homological mirror symmetry in this case. And I chosen this example because it's maybe is a case where when we can see a lot. So I claim that the normalization is already regular. And what is here Z1? So if I take x modulo y, so it is an element in the total ring of fractions. So actually, one can check it as a domain. And x modulo y to the square satisfies the following condition. So, and if I say x divided by y is equal to z1, then z1 is an element of the normalization. And now, let me just write you the map, and then you can convince yourself that everything works as I said. So it is a normalization of my degenerate cusp. So now, what is my conductor ideal? So again, another computation. So actually, what is a conductor ideal? So I can answer this question. So it describes the normal locus, let's say, but it's deeper than that. So it is. What? What is Z2? Well, I have. Well, Z2 is Z minus Z1. Well. Well, so conductor ideal is ideal in both rings. And it turns out that in R this ideal is principal, what is of course the case because it has codimension one, so it should be principal. And now, what are the rings involved here? Well, I have embedding of A modular conductor into R modular conductor. And if I heal X and Y, only Z remains. And here, this ring is Z1, Z2, modular Z1, Z2. With the embedding given by this rule. So now I can proceed to rings of quotients. Here I get my field of formal Laurent power series, and here the product. So it means that I computed all rings being involved here. And now, and also for future, let me use the following notation. I want to call the ring of formal power series phi d, and I want to call its field of fractions capital K. Now, what is an object of the category of triples? So I have to take a Cohen-Macaulay module over R. But R is regular, so I just have to specify the rank of a free module. Then next, I want to choose a module over Q of I bar, but it's a vector space capital K. So again, it's some number. Well, now the gluing map theta is a morphism of K Z1 times K Z2 modules. So theta is given by a pair of matrices of the same size. Let me write it like this. So I have the matrices, and the I, the matrix of size m times n over field. So here I abuse slightly my notation. So I write here KZ1, KZ2. The meaning is that I can forget the lower index. Maybe should. So it's my triple. So I take a free module, vector space, and two matrices of the same size. So there were these conditions in my category of triples, which I would like to state now for completeness. So conditions are the following. So having these two matrices, I can construct a new matrix, writing them together and writing them one above the other. And first condition, so surjectivity of theta can be translated that this matrix has full row rank. And injectivity of theta bar is condition that this matrix has full column rank. So it seems to be a very accessible kind of data. And now the question is when two such triples are actually isomorphic. Because we know if we want to classify Panoply models, it's the same as to classify isomorphism classes of triples. So what does it mean for two such triples to be isomorphic?
But didn't each of theta 1 and theta 2 are required to be surjective?
Huh?
Each of theta 1 and theta 2,
Yeah.
respectively, are surjective.
No, together. So the composed matrix. So it is a matrix of size. It is a matrix of size m and 2n. And this is a matrix of size n and 2. And we have this condition of ranks. So now, well, the key point. So when we want to speak about isomorphism classes of triples, so let theta prime be another. Well, if T and T prime are isomorphic, then of course ranks should be the same. So m is equal to m prime, n is equal to m prime. But of course, the essential information about module is contained in these two matrices. And the answer is that there exists a matrix Phi. And the condition is that theta 1 prime, theta 2 prime is equal to phi 1, theta 1, small phi minus 1, phi 2, theta 2, small phi minus 1. So my D is a ring of formal powder series. So if I have matrices over D, I can evaluate them at 0. And small phi is defined over the field K, is here. So if you translate what it means for two triples to be isomorphic, so you get this problem of linear algebra. So let me write it in the following explicit and elementary form. So I have two matrices of the same size over field K. Now I am allowed to perform arbitrary transformations of columns simultaneously. Transformations of rows are over D, but they are related so here it is phi is over K, and transformations of rows are over D. So I can perform arbitrary transformations of columns, of rows, in principle independently, but modulo the fields, they should be the same. So, after all, so the question is about normal form of such a pair of matrices. Well, maybe also taking this restriction on them. Well, and this matrix problem, well, resembles very classical problem in representation theory of algebras. And therefore, we called it decorated Kronecker problem. So Kronecker problem is a problem about the normal form for a pair of matrices over a field of the same size, where we perform simultaneously transformations of rows and columns. And there is a normal form found by Kronecker and Weierstrass in the 19th century. So here, it's a deviation from that. And it's actually the main point to classify Cohen-Macaulay modules over A. So if we can write normal forms for indecomposable objects in the category of triples, then we are done. And let me now write you the answer. So indecomposable objects are of two types. So there are continuous series called decorated bands, or simply bands, and discrete series called strings. So it is very common terminology in representation theory of algebras. So I have bands. So what is L and what is lambda is very easy to say. L is a natural number. Lambda is a non-zero scalar, and here I see actually I want to assume K to be algebraically closed for simplicity. So otherwise there is a small complication. And parameter omega is a sequence of integers of arbitrary lengths. So actually even natural numbers. There is two conditions. It is non-periodic. And if I want uniqueness, so I also require that for each pair, mi and I is a minimum of mi and I is equal to 1. And now I can even write the corresponding normal form. So there is a very pleasant way to write the answer. So theta 1 and theta 2 are square matrices. So θ1 is a block matrix, so identity times the mi. Well, θ2 similarly, and one place instead of the unit matrix, I put just a normal block. So well, it is a general normal form for continuous series, and for strings there is an analogous answer. So strings depend only on a discrete parameter. So it is similarly to omega, a sequence of integers. With the same normalization and normal form is as follows. So now matrices are no longer square ones, but have size t times plus 1. So I have to say that m0 is 1, something plus 1. Well, actually, maybe let me comment why we normalize here. So we can perform arbitrary simultaneous transformations of columns over K. So we can take, for instance, the same row in the first matrix and in the second and multiply it with some powers. We can achieve that n1 or m1 is 0. So that's going on. So it is the normal form, which in principle will give the classification of Cohen-Macaulay models. So recall what we actually classify. So we speak about Cohen-Macaulay models of degenerate cusp. Okay, so this may look like innocent, but actually proof of this and also of more general result carefully was the reason that it took many years to write the manuscript. So actually it is the hardest part of our paper. I'm telling you a joke. So when we got the main report for our paper, so it was very carefully written, and the comment was that concerning the matrix problem, so I think only the authors are able to follow the proofs, but we believe in the academical reputation and think it should be fine. I think it was a bit hard to say like this, I think. So actually we tried to write it in accessible way. And having a report like this, so nowadays many papers are declined even with very positive reports. I was very uncertain what's going to happen, but fortunately everything was okay. But still, so in homological mirror symmetry, well, involving time categories. Frequently, so there is this pattern, so strings and bands, and then you will see in the top of good mean. that you can speak about mirror symmetry and you write some curves on some surfaces, and then it becomes very geometric. And it appears at several places, but to my knowledge, in all the settings for mirror symmetry, actually the actual classification is done using the matrix form. And it's like a lower level programming, so you do not have enough tools to do, so it's indeed very technical thing. However, so here maybe you want to see modules, so I wrote you some canonical forms. Let me so just write the answer. So in the talk of Augusto, there was a discussion of Cohen-Macaulay modules of rank 1. So here, the Cohen-Macaulay modules of rank 1 are the following. So there is the normalization, and then there are two families. So, well, these are families of ideals depending on a natural number m and continuous parameter. So, and well, why is this? So R corresponds to this normal form, and then you have this, and you have dual situation. So in rank 1, canonical forms are quite easy. So here I do not remember. So is it m plus 1? So basically like this. So matrix of size 1 by 1, and some degeneration. Okay, so it is how it works for this degenerate cusp. So in the remaining time, let me speak about XYZ. So because it will be relevant for the talk of Kenzmin.
I think because you will erase that at some moment, I would like to pose a question I was leaving for
Yeah.
later. So, what happens if you consider a Yondim family? The Yondim series. So you take the non-isolated singularity,
Yes.
and now you add the power of a disjoint variable to some power of a not the of a transversal linear. And now the question is, can you find out which Cohen-Macaulay models extend to the deformation? So producing some a Cohen-Macaulay model to the deform.
Actually, thank you for this question. No, but it's actually interesting because so maybe indeed. So I wanted to say it, but I forgot.
And better put lambda in front of
Here.
No,
Here.
lambda times.
Yeah.
And now if you regard lambda as a parameter, then you have a space in one more dimension.
Yes.
That is fiber over lambda.
Yes.
And the precise question is if there is a Cohen-Macaulay model in the total space that restricts to one of these.
Well, we have not. Well, so here I think. Well, so you have a family. So general fiber is a cusp, and special fiber is the general cusp. Right? So we have not studied it, but it's of course a very valid question. and actually related to the previous talk of Augusto.
Because it kind of seems that if you put this M better with different name because there are two M's in the blackboard, if you put M prime and M prime is very large,
Yeah.
this maybe for M is small with respect to M prime, could be some chance.
Well, I must say, so I think that for this cusp, I think that in rank 1 there is only one family. But I mean, with Yuri, I think we once asked ourselves whether we can write this family, and we somehow,
So there is only one.
if I remember well. So I think that, so maybe Andras will tell
So
immediately.
this is minimal elliptic.
But if you put instead of 7,000,
No,
It
but,
doesn't matter, these
so-
are all cusp, minimal elliptic.
no, but Andras, so the exceptional fiber is a nodal, irreducible nodal curve for the 237. So, and then, well, anyway, so it turns out that for the generations, it's easier to write normal forms than for the isolated case. It's kind of interesting phenomenon. Okay, so
You mentioned mirror symmetry. Which mirror symmetry are you talking?
I am not going to talk about mirror symmetry, it's not my business, but it will be the talk of Kundmin. So, actually, Chalhun spoke about XYZ, and the mirror to XYZ is a pair of pens, and then it turns out that, so for XYZ, let me speak about XYZ. And for the generate cusp, the 2-3 infinity, so for this ring, so there is also a mirror. So there is a paper of Chalhun and his students, and there is a discussion. But it will reappear on Friday. And now, well, to conclude. So what happens to the degenerate types singularity T infinity, infinity, infinity? So the normalization is a product of three regularities. So conductor ideal A bar is equal to so, and when we take the total ring of fractions, then it is semi-simple. It is a product of three fields.
All three.
Yes, yes. So I so and here, so the map is given by a product of three diagonal invariants. Diagonal invariant of ky, you have diagonal embedding. For z variable, and you have diagonal embedding. Well, and also in this case, you get some problem of linear algebra where you can write normal forms. So, writing down the structure of what is happening here. So the logic is the following. So we want to understand Cohen-Macaulay models. We know that in principle it is the same as to speak about the category of triples. And in the category of triples, the essential information, in this case again, is contained in these gluing matrices. And here there is one category and the functor. So let me say that property of the functor E. So this functor preserves in the composability and isomorphism classes of objects. Well, and there is the following convenient way to speak about this category. So I think everybody must have heard about quivers, but this XA is so-called decorated quiver. And decorated means that there are two different types of vertices. So it's a cyclic quiver with 6 vertices altogether. 6 is 2 by 3. So 3 because I have 3 variables, x, y, and z. And well, recall that K is a field of formal Laurent series, and I have the corresponding ring of formal power series. Now, when we speak about quiver representations, then we attach to each vertex a vector space over K. However, in this decorated case, the notion of morphisms is different. So here, maybe the last for my talk. So if I have two such representations. So to any arrow, I attach a matrix of the corresponding size of but the kind of transformation rule is different. So these arrows correspond to my variables. So there is this labeling. And for bullet, I write a matrix phi over k. And for the star, I have two matrices. But they share the same value at 0. And now the condition is that u prime phi is equal to phi 1 u. And now the same logic applies to any map. So if we have v and v prime, then here I have some psi, and the condition will be y prime psi is equal to and so on. So I defined basically morphisms in my category of representations of the decorated field, so I can compose such data. And then I can classify again the corresponding indecomposable objects. And main theorem of Yuri and myself in this work is that all the general cusp singularities are Cohen-Macaulay data. And the main technique is to show that the corresponding matrix problem is a representation. So the general cusps are known to be Gorenstein, but not necessarily complete intersections. So we do not know homological mirror symmetry for them in the full generality.
What is then the definition of the generate cusp?
It's you who ask, so.
Yeah, but then it's, you say that it's Gorenstein not complete.
Again, so it's a definition.
Not.
No, it's a definition of Shepard-Baron. So it is. So these are singularities obtained by appropriate gluing of quotient surface singularities. So and then Shepard-Baron proves they are Gorenstein, and well, I think it must be known that they are limits of cusps. So cusps need to be complete intersections as well. Okay, so it's a main result. So thank you for your attention and attention.
Are there more questions?